Hey everybody, happy Wednesday. Good to have you back. Today we're going to go through 1.7. I don't anticipate finishing this topic. I'm going to kind of take my time in the intro part of this 1.7 topic, and then we will slowly but surely work through these problems tomorrow. Okay, so really 1.7 is going to span over 2 days. 1.8 will be next week Monday, and 1.8 is a very quick and short topic. And then next week, Tuesday, my plan is to review for a test on next week, Wednesday. Okay, so a week from today, we will have our very first unit test. I will be doing this on It's Learning. All right. I'm still working on the format. I'm still working out some kinks in terms of how that test is going to be organized. But it will be on It's Learning. It will absolutely be a timed test. For the sake of trying to prevent, cheating, obviously, and copying and people working in groups. But with that said, in your packet, okay, you have a review sheet or a review packet with an outline of all of the topics in Unit 1 and a whole bunch of practice problems, okay? I will be posting the answer key to that in the very near future, but we are getting close to our first test. And I would strongly recommend you start revisiting our early topics in this unit, topics 1.1, 1.2, and so on and so forth, and taking a peek at some of those practice problems. And again, eventually we'll be allowing you to, or I'll give you those answers and let you kind of go through your work and check your work on those things. So the other thing you'll see in there is there's actually two review sheets. One is called Unit 1 Review, which has, again, the first page of that is an outline of all of our topics and all the high points and all the things you need to know. The other review packet is called In-Class Review. Next week, Tuesday, the day before the test, we will have a live in-class review where we together are going through those problems and going through all those examples and making sure that they make sense, and I'm going to allow you guys to ask questions and things like that, okay? So keep that on your radar. I will obviously put that in the plans as well. Test next week, Wednesday. Again, today and tomorrow we'll finish up we'll finish up 1.7. Next week, Monday, we'll finish up topic 1.8, and then next week, Tuesday, will be a review day. Next week, Wednesday, will be the test. Okay? Topic 3 is due on Friday by midnight. After today and tomorrow's class, you should have everything you need to know to accomplish that assignment. Friday, we'll be doing a little lab activity again. I'll give you, again, probably, a half hour's worth of lab to analyze and look at and interpret the data. It's very similar to last week, so fear not. I'm not drastically changing the lab activity for this week. It'll be kind of a continuation or an extension of what I showed you last week in that video. All right, so let's get into 1.7 without further ado. I'm starting with this, okay? Which one of these is a PES spectrum and which one of these is a mass spectrum? In topic 1.2, we talked about mass spec. Mass spec was the instrument that showed us the mass of different isotopes, okay? If you go all the way back to 1.2, we had these graphs, and more often than not, they are bar graphs is typically how you see them. But every now and then, some of those mass spec readouts, or the spectra, can have these type of peaks, okay? And again, a mass spec shows the isotopes, so where these peaks fall would be different masses, and the height of these peaks would be like the percentage or the percent abundance of those isotopes. 1.6, the topic we just finished up yesterday, is on PES, which is photoelectron spectroscopy. PES is what shows us the orbitals within an atom, okay? So the orbitals are discovered or shown in these spectra by that instrument bombarding that chemical sample with so much energy that all of the electrons get released or removed. And each peak represents a different orbital. The x-axis is numerically backwards, okay, and that's the dead giveaway, by the way. That's how you want to use that's what you want to use to identify which of these spectra is each. But of course, I was a little mean, and I completely got rid of the numbers. All right. So here's my point with this intro question today. You can't really tell by just looking at the shape or the outline of the data. Okay, you have to go further. You need to observe the x-axis. That is the absolute best way to ensure that you understand what type of graph you're looking at. Okay, mass spec and PES have similar looking readouts. The way you can tell which one is which is by observing the numbers on the x-axis. Again, if it's PES, the numbers will be backwards. The large numbers will be on the left-hand side, the small numbers will be on the right-hand side. Otherwise, you can also look at the labels of the axes, right? In PES, the y-axis is usually called intensity or relative number of electrons, something like that. Okay? The y-axis in mass spec is going to be relative abundance or percentage. So the x-axis on these two graphs, PES usually says binding energy, and again, binding energy is how strongly the nucleus of that atom holds its electrons. For a mass spec, the x-axis would be mass, atomic mass. Okay, so there's a couple dead giveaways. Point being, please don't just look at the shape and assume you're looking at one or the other. You need a little more context to understand which one you're looking at, because if you get it wrong in terms of like what you're looking at, you don't have a chance at answering that question correctly. So just be careful. All right, topic 1.7, this is on periodic trends. We're looking at the periodic table, and we're going to look at a couple of trends that show up throughout the course of the organization of this thing. Okay, so the objective today, explain the relationship between trends and atomic properties of elements and the electronic structure and periodicity. Okay, electronic structure is of course related to the electrons. Again, how many electrons are there? Where are they located? Which orbitals are they in? And periodicity is just the fancy word of saying that like a pattern repeats itself. Okay? All right. So in chemistry, there's no greater tool than the periodic table of elements. This table is organized in a very specific way to group these based on their respective properties. All right. We've talked about this last year. Heck, we've talked about it this year. Again, point being, the organization of the periodic table is not random. It is well thought out. It is well organized, and there's many reasons why it is shaped the way it's shaped and why the elements are organized the way they're organized. So let's start with our very first trend. Our first trend that we want to look at is effective nuclear charge. Effective nuclear charge, we had talked about just briefly on Monday, okay, towards the tail end of that lesson. So effective nuclear charge is what the electrons feel, or the attractive force that they feel from the nucleus of the atom. There is a generic equation that we can use to roughly identify or roughly estimate what this value would be, okay? And that equation is, we take the number of protons that that atom has and subtract the number of core electrons that that atom has. So let's practice a couple of those now. So I'm going to take element 11, which is sodium. That's right here. Okay? And let's do this math for this particular atom. So Z effective, again, the symbol there is implying it's the effective nuclear charge, okay? And again, effective nuclear charge is what attractive force our electrons feel from the nucleus, okay? So how many protons does sodium have? Well, it has 11. Hold on. And how many core electrons does it have? Now, calculating core electrons is probably going to be tougher for you because, again, this concept of core and valence was just taught. So let's revisit that just for a second, right? If we look at the electron configuration of sodium, okay, let's do that, right? Let's write this out. Let's write out the electron configuration because that will absolutely help us identify which of the electrons are core and which of the electrons are valence. So sodium has 11 electrons. Let's go through that order, okay? To represent those 11 electrons in an electron configuration, we start with 1s2, 2s2, 2p6, 3s1. That's the electron configuration for sodium, okay? Now the question becomes, well, that's great, we have 11 electrons, but how many of those are valence and how many of those are core? If we identify the valence electrons, every other electron present is a core electron, okay? So valence, the definition of valence electrons, is these are the outermost electrons, okay? More specifically, in terms of using the electron configuration, the valence electrons are going to be our highest energy level, s and p electrons. So what's the highest energy level we reached? 3. Do we have s and p electrons in the third energy level? We do, just the one, right? So this right here is valence. Everything else is core. All right? That's a little lengthy to try to figure that out, right? But it's something where if you practice it, you'll be able to identify those core electrons much, much faster the more you do this, okay? So let's go back to our effective nuclear charge. It's element 11, we have 11 protons. How many core electrons does sodium have? It has 10, right? It has that one valence electron in the 3s orbital, but the other 10 electrons of sodium are core. So the effective nuclear charge for sodium is 1 plus. All right? Essentially what that's trying to say is that the valence electrons of sodium have a net attraction of 1 plus towards the nucleus. Let me explain that a little more in depth too. Okay? I have 11 protons in the middle. I have 10 electrons in the core. And I have one more electron in the valence. The question of effective nuclear charge is, what do the valence electrons feel as an attractive force from the nucleus? Well, let's assume we're a valence electron, okay? Do this weird thought experiment with me. We're a valence electron, and I am looking in towards the nucleus of my atom. And as I go inward from the outside of the atom towards the inside of the atom, I'm going to pass 10 negative charges. Those are the core electrons. And I'm going to see 11 positive protons in the nucleus. That's the positive charges. So I have 10 negative charges between me and the nucleus, and I have 11 positive charges in the nucleus. As a result, what I feel as a valence electron is plus 1. I feel one extra proton, or one additional proton in charge as opposed to the core electrons. Okay? So again, 11 in the center, 10 in the core, we're on the outside, 11 positives, 10 negatives, net is 1 positive. Okay? That's how we can think about this. Now, we're going to do one more of these a little quicker, but then I'm going to make this much, much easier and give you a general rule of thumb for the effective nuclear charge. Okay? So let me do one more. And let's do element, how about, I don't know, what is this, 13, 14? We'll do 14. How about silicon? Okay, we'll do element 14. So to do the effective nuclear charge of silicon, again, the math is the same. We would start with, I'm going to scroll down a little bit. Sorry about that. Okay, and I'll do this maybe over on the right-hand side. All right, so I have 14 protons. And now the question is, well, how many core electrons do I have for silicon, right? So again, we could kind of think about this and maybe figure it out in our heads. But let me just write it out for the sake of argument, all right? So the electron configuration of silicon is 1s2, 2s2, 2p6, 3s2, 3p2. Okay, sorry for having to bend it down there. This is the electron configuration. Now, let's go back to our definition of what valence electrons are. Valence electrons are the highest energy level S and P electrons. What's the highest energy level we hit? 3. Do we have s and p electrons in energy level 3? We do. These two and those two are valence. We have 4 valence electrons in silicon. Sorry, I ran out of space again. Struggling. These are core. So, silicon has 10 core electrons, exactly like sodium had 10 core electrons. In the same row, the elements have the same core electrons, okay? The core is really the electron configuration of the previous noble gas. What element has 10 electrons? Neon, okay? Ooh. Have you missed that sound? Neon is element 10. It's the previous noble gas. We have 10 electrons in the core for all of these third row elements, okay? So let's finish our math. We have 14 protons for silicon, we have 10 core, and our effective nuclear charge for silicon is 4 plus. Okay? So let me do this much more simply for you, okay? And this is going to be useful in 2 ways, hopefully. And again, I can't, my smartboard doesn't have the scroll bar on it, so I apologize. Let me run back over here and do this. In column 1, all of the elements in this column have an effective nuclear charge of 1 plus. In column 2, the effective nuclear charge is 2 plus. I skip all the transition metals because they are weird. And if you really want, I guess we can call this 8 plus, but we're not really going to look at noble gases very often. Okay? Long story short, across a row from left to right, column 1 has a 1 plus effective nuclear charge, column 2 is 2 plus, so on and so forth. Okay? Not only that, but if you remember back from last week, we also talked about valence electrons. And the columns also give you the valence electrons, and it's the same numerical value, right? In column 1, those elements have 1 valence electron. In column 2, those have 2 valence electrons. In column 3, they have 3. Column 4, they have 4. Column 5, they have 5. It's the same exact pattern. So for both the valence electrons of an atom and the charge, or I'm sorry, don't say charge. That's bad. It's not the charge. And the effective nuclear charge is 1, 2, 3, 4, 5, 6, 7, 8. Okay? Those patterns are the exact same. They're talking about different things, right? But they're related. So before we get any, I don't want to go on to the next one just yet, okay? Effective nuclear charge, just to recap, is the attractive force that the valence electrons feel from the nucleus of that atom. You can generically calculate it by taking the total number of protons that that atom has and subtract off the core electrons that that atom has. However, you don't really need to do the math because each column just successively goes up by 1 more. Okay? So I have a little paragraph here at the bottom which kind of summarizes some things, but if you understand how to qualitatively apply Coulomb's law, by the way, again, Coulomb's law is kind of a big deal. It's something that we use qualitatively, meaning we don't actually put real numbers into the equation. Okay? But Coulomb's law, just to recap, is this expression that explains how strong the attractive force is between 2 particles, positive, negative, or positive, positive, negative, negative. It doesn't matter. 2 particles. Okay? So really, effective nuclear charge is using Coulomb's law. We're looking at, okay, how many positive protons are there? How many negative electrons are there in the core? And then we do this simple equation to generalize that attractive force that the valence electrons feel. Okay? If I'm losing you, if this isn't quite making sense, I do strongly recommend kind of maybe going back to some old videos, rewatching the first part of this video, because there's a lot of kind of intertwined concepts here at play, right? So please hang with me, and again, I'm hoping that I'm making some sense to you guys. All right, the next trend one more thing. I'm sorry, getting ahead of myself. On these little mini fake periodic tables that I have here, or these blank periodic tables, we can draw in arrows to show which way the trend goes. All right, so the trend is going from left to right. Okay, whatever direction I'm drawing the arrow in, that's where it's increasing. As I go left to right across a row, there's a greater effective nuclear charge on this side. Okay, now up and down a column. In theory, again, if I were looking at column 1, these all have a 1+ effective nuclear charge. In reality, we can go a little deeper than that, and the ones higher up on that column feel a stronger effective nuclear charge than the ones on the bottom. And the reason why that is because higher up on a column, these atoms are smaller. So the valence electron of lithium, which is element number 3, the top one of that row, okay, the valence electron of lithium is much closer to lithium's nucleus. The effective nuclear charge is 1+, but that shorter distance makes that attractive force a little bit stronger. If I look at cesium, which is way down on the bottom left, or francium, okay, cesium or francium, which are way on the bottom of that column, they also have a 1+ effective nuclear charge, but their valence electrons are much further away because they're bigger atoms. So that extra distance makes that just a little bit weaker. The smaller atoms up on top of those columns have a slightly stronger effective nuclear charge if we're looking up and down, okay? Sorry about that, I didn't quite finish my slide. All right, now contrary to popular belief, I'm actually almost done for the day. I know I spent like 20 minutes on one slide, but I am almost done for the day, I promise. So let's do a couple more trends, and yeah, we'll pick this up tomorrow. So the next one here is size, the radius, atomic or ionic radii. Okay, how big are the atoms? Now, I just explained, and I just kind of talked about how as you go down a column, they get bigger. And that makes sense, right? That makes perfect sense. Okay? There's more stuff, right? If I'm in the first column, lithium has 3 protons, 3 electrons. Francium has 86 protons, or 87? 87 protons and 87 electrons, okay? That's a lot more stuff. I would have to imagine that francium's a much bigger atom, and it is, okay? As you go down a column, the elements or the size of the atoms get much larger. Now, it's the counterintuitive part. Radius, as you go left to right across a row, actually gets smaller. Okay? Let me give you an example. Let's kind of talk about that a little bit. If I'm comparing the size of sodium, we'll use sodium again, and I compare that to argon. Okay, sodium is element 11, argon is element 18. They're in the same row. One has 11 protons, 11 electrons. The other one has 18 protons, 18 electrons. Okay, so intuitively, your brain's probably thinking, all right, more stuff, bigger atom. And that feels like it should be right, but it's actually not correct. All right, across a row, atoms are larger on the left-hand side of a row, and here is why. In the same row, the elements have the same orbitals or the same energy levels, okay? So they're roughly the same size, more or less. But as we keep going across that row, we're adding extra protons to the nucleus. So here's what happens. Here's my sodium, we'll say it's this big. As I get to magnesium, I've added a proton, and it sucks it in, or the attractive force is a little bit stronger. Okay? Orbitals start kind of the same size, but that extra proton draws them in just a little bit more. I go to aluminum, extra proton, a little bit smaller. I go to silicon, a little bit smaller. Phosphorus, sulfur, chlorine, and then argon, right? So those extra protons draw in the outer electrons tighter and tighter and tighter across a row. Again, the key takeaway is that they start at almost the same size because they have the same types of orbitals and they're in the same energy level. But those extra protons, as I go across the row, keep drawing those outer electrons in tighter to make the actual atom smaller. Okay? So I kind of recap that here. So whenever you drop to a new row on the periodic table, you have added a new and much larger energy level to that atom. Atoms in the same row on the periodic table have their valence electrons in the same energy level and are comparative in size. And again, you can use the effective nuclear charge or the number of protons to figure out that as you add an extra proton across a row, they get smaller. All right, ionization energy. How much energy it takes to remove an atom's outermost electron. Okay, so in other words, we're looking at atoms and we want to remove one electron from those atoms. How much energy does it take to remove the first electron from all of these atoms? Okay. Now, a lot of this has to do with stability. Okay? Think about the types of ions that atoms want to form. I'm going to use sodium again. Sodium's been my go-to element all day long. Okay? So sodium is element 11. It has one valence electron. When it forms an ion, it gets rid of that electron and it has a 1+ charge. Why would it want to do that? Well, it wants to do that is because it becomes more stable when it has a noble gas electron configuration. Okay? Elements are the most stable when they have an electron configuration that matches the noble gases. So the elements on the left-hand side of the periodic table, which are the metals, generally lose electrons to end up at an electron configuration equal to noble gas. Elements on the right-hand side of the periodic table generally gain electrons to have an electron configuration that's equal to a noble gas. Now, when we're talking about ionization energy, this is how much energy it takes to get rid of one electron. The elements on the left, they want to get rid of electrons. When they become positively charged, they are more stable, and they generally end up with an electron configuration equal to a noble gas. So it's kind of easy to remove electrons on the elements of the left, but the elements on the right, they don't want to lose electrons at all. That's really, really tough to take an electron away from fluorine, for example, right? We know fluorine exists as a 1- ion when it forms an ion, fluoride. Have you ever heard of F1+, where fluorine loses an electron? No, I haven't either. It's not a thing because the amount of energy that it takes to make fluorine lose an electron is a lot. It takes a ton of energy to take an electron away from it. So here's the trend across the row. Okay, as you go left to right, it's harder and harder and harder to take electrons away from these elements. You can use the effective nuclear charge to make sense of this. As you go left to right, the effective nuclear charge gets bigger and bigger and bigger. 1+, 2+, 3+, 4+, so on and so forth. Okay? That extra positive charge that it feels from the nucleus means it's more attracted or more strongly attracted to the nucleus. Meaning, if I want to get rid of that electron, which has a stronger attractive force to its nucleus, I need to put in more energy to break that attraction. Okay? Up and down a column. As you go down the column, the atoms get bigger. The effective nuclear charge is kind of the same, right? We're calling that first column all 1+, but the atoms are getting larger and larger and larger. So if I try to take away francium's valence electron, it's very far from its nucleus. Because of that extra distance, because it's so much larger, it's easier to get rid of francium's valence electron than it is to get rid of sodium's valence electron. Sodium is much smaller, its valence electron is closer to the nucleus, and that distance, all right, less distance equals stronger attractive force. Larger distance equals weaker attractive force. That's Coulomb's law. That's a part of Coulomb's law, right? When charges go up, attractive force increases. When distance goes up, attractive force decreases, right? The things are further apart, there's less attraction between them. So, long story short, as I go down the column, the ionization energy is less and less and less, okay? So I want to draw my arrow upward. Again, all of the arrows that I've drawn in the last 3 slides are pointing towards increasing quantity of whatever we're looking at, right? So when I draw left to right on this one, I'm saying that the elements over here have a higher ionization energy. When I draw the arrow on the atomic radius from right to left, the elements over here are bigger, okay? So again, these are pointing in the direction of increasing value. All right, electron affinity, meh, we're not going to talk about it. It's not worth it, okay? It was an old topic that used to be a part of this class, but it's not worth your time. You can literally cross that off. Electronegativity, not meh, but not now. We talk a lot about electronegativity later in the year. It's not really worth it to talk about it right now. It just isn't. So it's a huge topic. It's a big deal, but we're going to skip that too, which brings us to a little summary and our first question, okay? Let me summarize for today. We'll call it a day. We'll do the questions tomorrow. All right, so understanding these trends and being able to compare two different elements off the periodic table quickly and without data is a very useful skill to have in this class. Focus on the effective nuclear charge. That'll more or less give you all of the other trends, okay? If you understand how to calculate effective nuclear charge, or if you understand that the effective nuclear charge is 1 plus 2 plus 3 plus 4 plus 5 plus all the way across, it helps explain why some atoms are bigger or smaller than others, the radius. It also helps explain why it's easier to get rid of some electrons than it is to get rid of other electrons. Okay? The effective nuclear charge explains both the radius trend and the ionization energy trend. So if you really focus on the first, the second and the third trend that I've shown you today can almost be explained by using the first trend. Okay? All right, I'm all done. That was a little longer than I wanted to, but I'm hopeful that my long-winded explanations were clicking for you guys. Have a lovely day. We will catch you later. And if you have any questions or if you need anything, please don't be shy. Pop into my office hours, shoot me an email, and I'll be happy to help you. Have a good day, guys.